Log on, tune in, find out. Another good idea from Cambridge.
Particularly warm welcome to, and it's going to be warm as well, to all of you who are new to the Newton Institute. I'm David Wallace, I'm the director of the Institute. You really have a great programme lined up for you, a very intense one, that's going to keep Steve Greenham, who's recording in the tiny studio at the back here, on his toes for many, many happy hours during the next 5 days. I'm going to just say just a few words. First, obviously, is by way of thanks. It's thanks to all the organisers of the programme, the DISC programme as a whole. That's Rod, Frank, Reinout, Oscar, and Masatoshi. I'm really grateful to the whole programme. Wouldn't have taken place without them, and I'm really grateful to them. And of course, for this particular workshop, Rod and Masatoshi are involved, but particular thanks to Peter and to Adri as well for helping to organise this workshop. I think we're probably going to be pretty busy this week as well, because it's also the start of a new programme in Modelling the Heart, the Cardiac Physiology, which is a 1-month programme. So the staff will be quite stretched with all this, but if you're there, the sole purpose here is to help you have an interesting and stimulating and fruitful time. So if you have any questions whatsoever, please just go to the desk, and I'm sure they'll try to do the very best that they can to solve any problems that you might have. A final comment, if I may. You see the sign about switching off mobile phones. It's not just an issue, if you will, please, of putting them on silent. And I suspect this also applies if any of you have got a laptop with a card in it. You should switch them off, because the microphones will pick up the and you'll get it in the recording. All of this is going to be, with the permission of the speakers, is going to be recorded on video for posterity. So anyway, I hope you will do that, please, because it is quite noticeable when it's picked up by the microphones. But apart from that, I just say, well, have a great week. Enjoy, and I hope it's a really useful and interesting time for you. Thanks again.
Thank you, David. For those of you who don't know, I'm Peter Clarkson, the organiser of this workshop here. Before we get to the first talk, I'll just say there are 2 changes in the programme. Claude VLA, unfortunately, is unable to be with us at this workshop, so Willie Herman will talk at 2 o'clock this afternoon. And then on Thursday afternoon at 4:30, Nicholas Witt will talk then, rather than on Friday afternoon. So, it's a pleasure to welcome Simon Rosenhout from Leeds and Loughborough, who's going to give the first talk on Hilbert-Schmidt operators versus elliptic Calogero-Moser type systems. Thank you, Peter.
So, I should be audible via the loudspeakers now. This talk is about elliptic Calogero-Moser type systems, and that's why I will start by reminding you what they look like. There is the non-relativistic elliptic Calogero-Moser system, given by this partial differential operator. Here we have the free kinetic energy, here we have a sum of pair potentials. The coupling constant is parameterized in a somewhat unusual way. Those of you who have seen the operators and their properties before will know why. This is the simplest way to get the eigenfunctions have a nice dependence on the coupling constant. And actually this particular dependence will be a consequence of the non-relativistic limit, because these systems have a relativistic version. And then the dependence on the coupling should be as simple as possible, and from that simplicity this particular non-simplicity derives. So notice that there are 2 values of the coupling constant where this is free. It's G is 0, but also G is 1. Now we are interested in the Hilbert space theory of this operator, not just as a partial differential operator, but as a Hilbert space operator, and that's why we insist that it be at least formally self-adjoint. So we need the coupling to be real, and we want the p function to have a real period pi on r and an imaginary period I alpha. So r and alpha are positive numbers. They will reappear at several places. At the relativistic level, there will be two such alphas, and there will be a symmetry between them. So that's on later slides, but I'm now already saying this. At the non-relativistic level, we need only one such alpha, and at the relativistic level, there will be two of them. Now, this is an integrable system, which means that there are further commuting partial differential operators, which have higher powers of the momentum operators, right? These are just this is just the jth momentum operator of the jth particle. And the second one is nothing else as the operator you had here. They all commute, and that's why you're dealing with an n-particle integrable system. Now, if you're not familiar with the p function, I suppose most of you are, then think of this as something with the same graph as 1 over sine squared. If you have 1 over sine squared, actually you know all about the Hilbert space eigenfunctions of this set of operators, because then you can solve it in terms of the Jack polynomials or Sutherland polynomials. And so in that case, the Hilbert space theory is well understood. And the name of the game is here to understand this elliptic generalization in as much detail as possible. It's very unlikely that you can get the same detail as the trigonometric regime where you have two orthogonal polynomials, but we just want to go as far as possible. So the relativistic generalization is in terms of n commuting analytic difference operators. So here we have the momentum operator in the exponential function here, which means that you are shifting into the complex plane. Beta is positive. Physically speaking, it is 1 divided by c, the speed of light, so this is a positive quantity. And you notice that when c goes to infinity, beta goes to 0, and you have to Taylor expand this to get back to the previous non-relativistic integrable system. So here we have a time translation generator that is gotten by taking the sum of S1 x and S1 minus x, where these functions are defined here. These analytic difference operators are up here. You take here now an index subset of this set which has cardinality 1. So here we have just one of these indices, and here we have the interaction function, which is in terms now of the Weierstrass sigma function. So if you take the product of this f plus and f minus function, then you can express that again in terms of the Weierstrass p function. And it is clear from the appearance of beta that for beta to 0 you can expand this, and you sort of see already that when you do this, that you will get this previous sum of paired potentials. I have not worked it out here, but that's really a quite simple exercise. So for the momentum operator, it's even simpler, because here you're taking the difference of the two, and then you just pick up from the exponent here the sum of the partials with respect to the jth position, and that's nothing else. It's a non-relativistic momentum operator. Here is the boost, the Lorentz boost, and that remains the same. It just becomes the Galilei boost when you take speed of light to infinity. Okay. Well, that's one version of these systems, which is associated to the Lie algebra an-1. That has while group Sn. You have permutation invariance in the n positions. Here we have a generalization where you have not only permutation invariance, but also invariance under sign changes. So you can flip signs here at will. You get the same Hamiltonian. This generalization is due to Inozemtsev, and he found the Lex matrix at the classical level and therefore integrals, but to show that they commute and also at the quantum level you need more work, and that was done by Oshima and co-workers. So here again there is a relativistic version. Now relativistic is not quite the right word here. You have external fields, but it's convenient to refer to it that way. It's a difference operator version of this integrable system which involves differential operators. Here, however, you cannot easily write down these commuting analytic difference operators. Their existence is known from work by Komori and Ikami, but it's sort of quite difficult to disentangle explicit expressions from their work because it's in terms of some rather high-powered R matrix technology. You can write down the defining operator, however. That was first done by Van Dien. He introduced this relativistic version. And in this case, the defining operator is a one-parameter generalization of the Kornminder operator, which refers to the trigonometric level. So there again, at the trigonometric level, you know the Hilbert space theory quite well. It's in terms of the McDonald Kornminder polynomials. The an-1 case, I forgot to mention that, at the relativistic level involves the McDonald polynomials for that root system. And of course there are McDonald polynomials for arbitrary root systems, but Kornminder was the first to extend this picture to the BCN case. So we now want to say a little more about the goals of this enterprise. I already said you need to view these commuting operators now as self-adjoint operators on a Hilbert space that commute, which is a much stronger requirement. And the Hilbert space at issue here is over these sets. They're fundamental domains for the well group action on the torus, on the N torus. So here we start from 0 because we have invariance under sign changes, but otherwise they're quite similar, these two sets. Well, you want to show that there exists an orthonormal base of joint eigenfunctions with real eigenvalues. That's the picture you have for the trigonometric level, and you expect it to extend to elliptic level, because the potential, physically speaking, is exactly the same appearance, the same qualitative properties as for the trigonometric case. And this then is what you should be aiming to show. Now, and then the third goal is to look for transformations, if any, on the coupling parameters that leave the spectrum invariant. So these are the goals. And how are we going to go about achieving these goals? Well, there is now a new ingredient that is really quite surprising. The existence of this new ingredient is really sort of begging for a deeper explanation. It is the existence of integral operators that are very intimately related to these commuting operators. So I'm just writing down here the properties that they have. We'll see them in detail later. First of all, they're Hilbert-Schmidt. So they have kernels that are square integrable over these fundamental domains F. And they are related to the Hamiltonians via these formulae right here. So in the an-1 case, you have the same Hamiltonian acting on the x variable and the y variable. In the BCN case, however, you need to take not the same Hamiltonian, but rather the Hamiltonian where the set of couplings is changed in general. It can be the same, but in general it will be different. That's because the p prime is a linear function of p, and you saw for the Inner-Zemtsev case that there are 5 couplings around. There are only 4 if you have rank 1. For the Van Dien case, there are actually 9 couplings around, 8 of which are external field couplings. So as it turns out, in the rank 1 case, you can take these couplings arbitrary, but for higher particle number, higher rank, there is a linear relation that expresses the extra coupling in terms of the previous ones, in terms of the external field couplings, the balancing condition. Again, that points in the direction of there being some deeper reason for why these simple integral operators exist, but that hasn't emerged so far. Although I should already mention that in the rank 1 case there's actually a relation with the Pain-Levé world, with P6 in the case of the differential operators and with the elliptic Sakai system in the case of the difference operators. I'll come back to that. Okay, what's the crux of this? This is just an algebraic fact. You can show that this is true for the kernel. It just involves function theory. There's no Hilbert space theory involved at all. This kernel is just a zero eigenvalue eigenfunction of the difference of these Hamiltonians. And at face value, that seems to have no bearing at all on the Hilbert space theory, that fact. But the point is that it turns out to be possible to reinterpret these relations as commutation relations in the Hilbert space. The range of this Hilbert-Schmidt operator is going to tell you how to define the domain of the Hilbert space operators that you want to associate to these differential operators or difference operators, depending on the level. And that, especially in the case of the difference operators, is already something very non-trivial, because they shift into the complex plane, so that they don't like to be acting on L2 functions on the line. They will not have generally analyticity properties at all. So you see right away you're dealing with some rather singular operators. They will only have a dense domain of functions that allow shifts into the complex plane. And so the issue of domains arises, and it turns out to be a very, very non-trivial issue that has not been studied in general in the literature. So it's a great help that these integral operators are telling you what sort of domain these operators want to act on. Well, it is with that interpretation of the operators as at least symmetric Hilbert space operators that you get this commutation relation. So the hat on the operators here indicates that now you're reinterpreting them as Hilbert space operators. And there's many ways to do so. You know that already for the Laplacian on an interval, right? You need boundary conditions to turn it into a well-defined Hilbert space operator. And depending on what boundary conditions you pick, you will get different spectra. So there's a whole raft of Hilbert space operators associated even with the free case, the free Laplacian. And once again, as it turns out, these integral operators just are going to tell you what domain to pick. Okay, so what is the other tool? The kernels, as I said, are very simple, much simpler than the operators. In the analytic case, in the analytic difference operator case, they're just products of elliptic gamma functions. And in the non-relativistic differential operator case, they're just products of Jacobi theta functions. And that you can understand from the elliptic gamma function satisfying a difference equation with a right-hand side that's basically a Jacobi elliptic function. But to have the elliptic gamma function in a form that is particularly suitable for these Hilbert space applications, you quickly led to sort of modified theta function. And you need two of them, because as I announced, there are now going to be two alphas, which I'll indicate as A plus and A minus. The alpha in the analytic difference operator you saw in the relativistic case is one of the parameters A plus and A minus, and the other one is beta, one on the speed of light. Recall that when you saw the set of commuting analytic difference operators, the alpha and the beta appear to be on a completely different footing. You were shifting over distance beta into the complex plane, and that's the beta parameter. The alpha parameter is buried in the interaction. It gives the size of the imaginary period. So they look completely different, these two parameters. And it seems very strange that you should be aiming for eigenfunctions of this set of operators that are actually symmetric under interchange of these two variables. But that's what the kernel is going to tell you, because it's all in terms of this elliptic gamma function, and you see that there is a manifest symmetry between the interchange of A plus and A minus. And this commutation relation we will again reinterpret as there being a joint orthonormal base of eigenvectors for the Hilbert-Schmidt operators and for the Hamiltonians. And since the Hilbert-Schmidt operator is invariant under the interchange of A plus and A minus, this will also be true for its eigenvectors. And that's why the orthonormal base of eigenvectors you need for the analytic difference operators will actually have this A plus A minus symmetry. In other words, it will also be an orthonormal base for the analytic difference operators where you interchange these two quantities. And you can check explicitly that yes, that set of difference operators commutes with the previous ones as difference operators. That's of course a necessary condition. Well, so we have this right-hand side function in terms of this infinite cube product, and the other function that we will employ is again a Jacobi theta function. It's the odd Jacobi theta function, but it's normalized differently. And because we again need two of them, one for A plus and one for A minus, we use this abbreviated notation with the delta taking values plus and minus. And so these are the principal actors in this story. These three functions will reappear all the time. And the reason for choosing S here is that this reduces to the sign in the trigonometric limit and to the sinh in the hyperbolic limit. And this is the right-hand side function of this analytic difference equation. And I should perhaps also mention that if you pick one of these analytic difference equations, so you fix delta, then you can simply ask what is the simplest solution of that analytic difference equation. Simplest can be given a precise sense, and it turns out that in that precise sense the elliptic gamma function is the simplest. That same notion singles out the Euler gamma function via its functional equation that everybody knows about. Fz plus 1 is z fz. That's the functional equation for the gamma function. But again, there's an infinity of solutions there, because you take the gamma function and multiply it by any function that has period 1, meromorphic function with period 1, you get a new solution. And you can again ask, why is it the gamma function that we're always using? Well, it's this notion of minimality, of optimality, that gives you uniquely the gamma function, and it is the same notion that gives you the elliptic gamma function. And the surprise is that at this elliptic level, that function is actually symmetric in the shift here and the delta that occurs in the right-hand side function. That's by no means obvious when you look at the difference equation. Anyways, there's probably more to be understood in this whole story. So let's now turn to the an minus 1 case. First of all, we have these square roots in the potential functions. You can get rid of them by making a transformation with the weight function. So the weight function is defined in terms of the C function and Harish-Chandra function, which is again product of G functions. these g functions downstairs can be easily moved upstairs, because the elliptic gamma function, as I defined it, has a very simple reflection equation. If you take g of minus z, then that's the same as 1 on g of z. That's the generalization of the Euler reflection equation for the gamma function, the rational gamma function. And that means that whenever you see somewhere a g in the denominator, you can actually easily put it upstairs by having all minus signs, right? So here I have explicitly indicated the relation to the previous parameterization. This is the alpha that we had, the original imaginary period, size of it. Here is beta, 1 on the speed of light, and now we switch to purely imaginary coupling constant, which is product beta g, okay? Now, the upshot of this transformation then, if you omit some multiplicative constants, is that you get these expressions. There are n of them that we had already, but then we can now switch the a plus and a minus around, and then we get n further of these operators that commute with the given ones, as you can easily verify. These coefficients aren't quite elliptic. There's a constant multiplier, but that's why they commute, right? There is another gauge transformation that actually makes the coefficients elliptic, and then it's clear that if you have this shift doesn't see an elliptic function with that imaginary period. If you shift it through, nothing happens. So that's why they commute, okay? Now, what then are here these kernel identities? Here is the basic the non-trivial building block of the kernel. It's this special function here. And the point is that this satisfies these difference equations here. So the special function is a zero eigenvalue eigenfunction of this difference of analytic difference operators. And actually you can also take here plus and minus plus. So there are 4n altogether. But taking this other sign here is not really giving you new operators, because they're related by the product of all these shifts. Okay, so there are really 2n independent ones. Well, if you shift just the xj's by the same complex number xi, then you see right away that this still holds. So there's actually a one parameter family of these kernels. And what you can do moreover, this is a little, well, you don't see it perhaps at a glance, but it's still at this algebraic level easy to see that you can multiply also by an arbitrary function of this structure where phi is meromorphic. I will say something about how you prove this in the BC case. I don't want to repeat the ID. So how do you get from this to the non-relativistic world? Well, remember that mu was I beta g, so now we just let this beta go to 0. Where is it? There. And we revert to calling a plus alpha, okay? And then we don't need these deltas anymore, because now we're throwing one of these positive parameters away, okay? So that's why there are no deltas anymore here. That you get this limit it's quite plausible from what we know already about the elliptic gamma function. When g is equal to 1, you need not take a limit, because then you just have this quotient of g functions, and you see that it's just the analytic difference equation that tells you that it's equal to this for g equal to 1. More generally, if g is integer, you can use the analytic difference equation for the elliptic gamma function to express the right-hand side in terms of just the r function, and then it's quite simple to see that when you take a minus to 0 that you get this function here. So for integer g, this is very easily established, and it is the case where g is not integer where you have to do work. You have to look at this limit for the elliptic gamma function and once and for all show that it involves this branch point, this logarithmic branch point. The appearance of these branch points can be understood from the fact that you're dealing with sequences of poles and zeros whose distances go to 0 as a minus goes to 0. And so this line of poles or zeros, as the case may be, is condensing into the cut you need for this multivalued function. Okay. Well, the weight function takes on this simple has this simple appearance where p is an infinite Q product that will appear later on. It's gotten by switching from R to S, which is much more natural here. You see right away that this is positive on F on this fundamental set, and you're taking here the positive branch of the logarithm. So this is a nice weight function indeed on F, and it reduces to just product of signs in the trigonometric limit. So that is the weight function for the Jack polynomials. Now how about the kernel? Also the kernel has limit expressed solely in terms of these S and R functions. So upstairs we have the limit of the weight function, right? Weight function x, weight function y, and downstairs we have of course the limit of the special function. And so for the Hamiltonians we get these relations. And in particular, if you look at the defining Hamiltonian, so that's just kinetic energy plus sum of pair potentials, then you get an identity that was first obtained by Langman, and just like I obtained the more general identities via a detour. I wasn't really looking for them. I was trying to solve the elliptic difference Schrödinger equation, and sort of realized that I couldn't do it that way, but then found these kernels. He was doing also something very different, looking at quantum field theory of anyons, and saw that there is some identity emerging there, which he then used in a quite different way. He used it to set up an algorithm to find elliptic eigenfunctions perturbatively by using what you know about the trigonometric case. So that's another way of using these identities, but it's far more involved, and it doesn't actually say much about convergence. This tack is leading to technicalities that are really quite hard. Whereas if you reinterpret these kernels in terms of Hilbert-Schmidt kernels, then you can actually put them to much better use, as I hope to convince you. Okay, we are now turning to the free cases where you get non-trivial information for the an-1 case. You see the obvious free case where the coupling is 0, or mu is 0. There this kernel is useless, because remember, for instance, for the non-relativistic case, you had well, no, I'm mixing up things. Yes, let me put it this way. There was this quotient of g functions which had plus mu on 2 in the numerator and minus mu on 2 in the denominator. If you put mu equal to 0, you get 1. Okay. Now 1 is a kernel that's certainly Hilbert-Schmidt, but it's rank 1. So it just tells you that yes, the function that's constant is a joint eigenfunction of this Hilbert-Schmidt operator and the Hamiltonians, which is not so surprising because the Hamiltonians reduce to sums of partials, which annihilate constant functions, or then sums of analytic difference operators, and they don't shift constants. So it's an obvious consequence you have there. It doesn't tell you anything about the non-trivial eigenfunctions. It tells you about one eigenfunction, the ground state. So that free case is uninteresting. It's the g equal to 1 case, which is also free for the analytic difference operator setting. That's far less clear, but it's true. We'll see it soon. That's the case where the Hilbert-Schmidt operators are non-trivial, and where they sort of explain better what is involved in using them to promote the difference operators and differential operators to Hilbert space operators. Because remember, there was this domain problem. They're not at first defined as Hilbert space operators. You have to be clear on what domain you need. And that's the lesson that we will draw from them here. So here we simply have these differential operators, and if you undo the similarity, which is simpler in this case, does not work with the weight function, then you get just up to a constant sums of shifts, products of shifts. So that's also a free operator. It doesn't involve x-dependent coefficients. This is from mu equal to I a minus, but you can just as well choose this mu. You get the same operators. There's actually a symmetry in mu. I'll come back to that. Now, in both cases, you get the same kernel. The a minus dependence goes out, so you should now view the a plus as alpha in the differential case. And it's clear that we are dealing here with the Hilbert-Schmidt operator. You can also see that when psi is imaginary, then it's self-joined, whereas otherwise it's a normal operator. You can readily verify that you get commutativity. So you have altogether a commuting set of normal Hilbert-Schmidt operators, and that means you will get, if there are no spectral degeneracies, you will get a unique orthonormal base of joint eigenvectors for this commuting family of Hilbert-Schmidt operators. Now, these spectral degeneracies are actually the main, or well, not the main, it's one of the difficult technical problems in the elliptic world to show that there isn't spectral degeneracy, or rather, that there isn't an infinite dimensional null space. Because in the trigonometric case, there is an infinite dimensional null space. This tells you that you cannot count just looking at the form of the operators on there not being an infinite dimensional null space. And it's very likely that the null space at the elliptic level is actually always trivial. And therefore also the range is dense, because taking the adjoint is just taking psi to psi star. From that you can conclude that the null space and the range problem are exactly the two sides of a coin. Okay? And why is it that you want the range to be dense? Well, remember, we want to define the Hamiltonians, and then you better have a dense range telling you what sort of functions you need in a dense domain, the dense subspace of your Hilbert space where the Hamiltonians are defined. Right? If there would be big null space, you cannot say anything about what these Hamiltonians are doing on it, except that they leave it invariant. But that's just not enough. Now, as it turns out, you can handle the case where you have a finite dimensional null space, and what we will see explicitly in this case is that in this case you get actually a trivial null space and a dense range, because here it turns out that you can solve the eigen function problem for the Hilbert-Schmidt operators, and it's not so hard to do really, because we already know that we should aim for joint eigenvectors. So you just look at some obvious basis for the free Hamiltonians and how they match with the range of the Hilbert-Schmidt operator, and then you quickly see, this is what we need. This is what we need. These are, in physical parlance, the orthonormal base functions that correspond to free fermions with periodic and anti-periodic boundary conditions depending on the parity of n. If you would still have the weight function around, then this would be divided by the expression you get when you put n equal to 0, and then these are nothing else, just the Schur polynomials. So also from the mathematical viewpoint, these are well known, these functions. And well, the point is now that this is also the this is one way to turn these operators into self-adjoint commuting Hilbert space operators, but this is the way you need for it to be compatible with the Hilbert-Schmidt operators. So the Hilbert-Schmidt operators have a uniquely determined orthonormal base, and it is this one, and then that tells you that this is exactly the way that you need to turn the differential and difference operators into self-adjoint operators, namely by having them act on this base. And of course you get real eigenvalues if you act on this base that you can just read off, because these are just plane waves after all, just antisymmetric sums of plane waves. So here you have the desired reinterpretation. Now you can very easily see what the psi dependence of the eigenvalues of the Hilbert-Schmidt operators is. You can take this out of the eigenvalue equation, and so you wind up really with these unknown quantities, and they're not explicitly known, but it can be shown that these are actually non-zero, and that you get by having a very, very special function of the previous type that we saw already doesn't spoil the kernel identity. The point being that you look at this kernel and you see that it's really very close to the elliptic Cauchy determinant. You need just two factors up front to turn it into an elliptic Cauchy determinant, and you can exploit that by picking this function psi, which you can by and large choose arbitrarily, in a very special way, and then it becomes the elliptic Cauchy determinant, which means it's the sum of products, and then you can do the integrations and get explicit eigenvalues. Now, of course, this was the intuition of why you can do it, but actually you can also turn it around, because if you look at the multiple integrations carefully, you see that they can be performed recursively, and actually that gives the umpteenth proof of the Frobenius identity, of the elliptic Cauchy identity. It's independent of all previous proofs. So what is the main bonus of this free case is that you now have eigenvalues explicitly for a special case, and from there you can show that these eigenvalues must be all non-zero. And remember, this is the kernel property that we needed to sort of have in our hands for these kernels to be really useful. Right? Now we have it for one set, for one value of the coupling, but now we can use things like the analytic fratron theory and stuff like that to sort of see that generically you will have only finite dimensional kernel on an exceptional variety. So that's the use to which this can be put. Now, how about the BC cases? Here you deal with, for arbitrary n, a much harder problem, I think. But for the rank 1 case, you can get much farther. So here we now switch to a one variable setting, one particle, an external field. So there are 4 different couplings here, and this is nothing else as the Hoyne equation when you look at the time-independent Schrödinger equation for this operator. Now, this is clearly formally self-adjoint. Remember, you have these reality conditions, so that's okay. And also, you see right away that formally there is no difference in this operator when you take the g's, when you reflect the g's in this way. But the g0 and g1 multiply functions that have poles on the real axis. So that gives you potentials that are unbounded. And as it turns out, in the actual Hilbert space version of these operators, these two invariances break down because they're different self-adjoint extensions, and you jump on another branch, so to speak, as you go from one value of g to the value 1 minus t for t is equal to 0 and 1. Whereas if t is equal to 2 and 3, then you have the wiggle p function, right? You're shifting up in the complex plane, so you have the smooth wiggly p function, and that's a bounded multiplication operator. So there, yes, you will get these spectral invariances, and they're trivial because the domain is not influenced by adding something bounded to a symmetric operator. So that's why they will be there, these invariances. Now the kernel is now in terms of this weight function. Here is the corresponding Harish-Chandra function. And the explicit form of the kernel is here as follows. You have now this G prime, which is given in terms of a reflection of the G's. And here we have a sum of the G's. And you quickly see that's just the same as the sum of the G primes. And because we have these weight functions involving basically the odd elliptic, the odd Jacobi elliptic theta function, you must ensure for square integrability that you don't have too serious a singularity at the edges of the interval, right? So I mean, that's just like when you would have 1 on sine, or rather sine to the power g0, you need g0 to be bigger than minus 1/2 to have square integrability at the edges of the interval, right? So that's where these conditions come from. The eigenfunction property that we need, the difference eigenvalue property, is now encoded in this functional equation here, which looks rather ghastly. There are second order poles in all the terms. Here we have logarithmic derivatives of these theta functions, so you wind up with shifted Weierstrass zeta functions, shifted by constant or other linear function, because we went from the sigma function to the s function via the quadratic exponential. So it's only because you expect this to be true that you start proving this functional equation, because it certainly doesn't look to be 0, the right hand side, but you expect this to be true because at the relativistic level there was an identity that you could prove more easily, and then if you take the limit of that, you get up to some gory constants that you cannot really nicely control. You get this, so you expect it to be true, and yes, it is true. And you do it by just looking at the principal parts, at all these poles that you see there, and showing that they cancel, and then because stuff is elliptic in x and y, you know that at least this right hand side is constant. Now then it is a matter of choosing x and y appropriately, which you're allowed to do because the right hand side is constant, and taking further limits, because it doesn't work in one fell swoop. Actually the second part is more laborious than the first, and then in the end that constant is 0. Now the functional equation for arbitrary n is even more gory, but also there you get constant 0, and once again you would never arrive at these functional equations if you wouldn't sort of see that they have to be true up to constants by starting at the relativistic level and taking limits that you cannot completely control, but to such an extent that you're confident that it should be true, and it is true. Now, for this case, actually, the identity can be shown more easily by going over to rational coordinates and sort of peeling off factors, and it has appeared in a quite different context in work by Kazakov and Slavianov. So that is in the tradition of finding kernel functions of the Hoyne equation that goes back to work of Erdely 60 years ago. So that's something I only got aware of rather recently, that there is this previous work where you also connect functions of Hoyne type by means of a kernel, and Erdely first found a kernel involving the 2f1, the Gauss hypergeometric function. And ever since there's quite a slew, a whole raft of kernel functions that have been found, and this one by Slavianov and Kazakov was in that program, emerged in that program, but in their book, or rather in their paper later on, it's also in the book by Slavianov and Leeds, it's really not made clear where they got it from. It just is there, and they gave a proof that's simpler than the one when you use the elliptic functions. But once again, you would like to understand it in a more conceptual way. And this is the point where I very briefly will mention that it also shows up in Pan-Levy theory, in the theory for P6. This was shown not long ago by Takamura, but I have no time to go into that any further. So also there you get a lead for what might be the case for the multivariable case, but it's sort of very indirect way of getting to this kernel. It's still not probably the right way to look at it. Anyways, so let's now turn to the relativistic case. So I'm sorry, first of all, we have this problem of still figuring out what is the spectral invariance. Well, first of all, we want to insist that the sum of the g's is positive, because only then can we show that this kernel, the null space, is actually trivial, and therefore also the range is dense. And that's because here you can actually use the Stone-Weierstrass theorem applied to p-function powers, and what's very important that you need positive coefficients, and the positive coefficients are guaranteed by this condition. It's probably still for SG smaller than 0, there's a range where it has trivial kernel dense range, but that's really conjectural. It certainly is not true for SG equal to 0, right? Because that was the case, remember, where the kernel becomes trivial, where you have rank 1, right? Which is very far removed from having trivial null space. It's the auto complement of the constant function, which is the null space in that case, right? Now, here is what you can conclude from the Hilbert-Schmidt property. There are singular values like this. Their square sum is finite, and here are the orthonormal bases. So if you're not familiar with this singular value representation of Hilbert-Schmidt operators, then you can just as well replace this by I star, and then you get just one of these bases. I star I is the other basis, so it has to do with the polar decomposition. And these nu's are actually very likely exponentially decaying, so that you're dealing with trace class operators, not just Hilbert-Schmidt. In all cases where they can be calculated, they're actually exponentially decaying. Now, here's what happens. You can introduce new couplings like this, so that you get a certain polytope where you get invariance in terms of these couplings, and you get actually permutation invariance. You can take arbitrary permutations of these C's, and the point is that you have the two trivial symmetries. They are transpositions of these sets of C's, but there is also this this extra J map, and that's going to be just the transposition that you need to complete the S4 invariance, right? If you have these three transpositions, then they generate S4, and so in terms of these variables, you get something that you wouldn't expect at first, because it doesn't look like spectral invariance at all, and that's most clear for the case where the G's give you a free theory. Then you have just a free Laplacian, right? Where's my light? Here. So there's 16 cases, and now you can readily see that here you have actually Neumann conditions at the end points of your interval. Here you have the Dirichlet conditions, and here you have Neumann-Dirichlet at the two sides of the interval. So the eigenvalues for H are of course obvious, but you can also determine the eigenvalues for the Hilbert-Schmidt operator. And that's on the next slide. Here are some cases that you can handle, and the eigenvalues don't give you a clue as to what the general structure of them might be. That's a pity, because you would like to sort of have an educated guess for what the general eigenvalue would look like, but it doesn't seem to emerge from these special cases. Now here is what I said before. I mean, you had a free operator, and this is the transformed operator. So here you have obviously a very singular potential, right? You have a singularity like this at one end of the interval, and at the other end you go down into the cellar. So this operator has actually free spectrum. Spectrum is the same as the one that you started from, which was free. And these are the eigenfunctions. Now here's a case where you actually don't have eigenvalues, but singular values, and they're positive and can be evaluated again, right? Here you have the case where you have two different OMBs of your Hilbert space that are related by the kernel, and these singular values are actually positive. So they are, that's probably true in general, but that's again something that's unknown. Now let's then now turn to the relativistic case. Here we have a very complicated operator. The C function you need is simple. You also need the scattering function in this setting, and here's the weight function again. And this scattering function is actually unitary. It's a phase on the real axis, which means that this similarity transformation is actually unitary when this is a genuine Hilbert space operator, right? Because these are phase factors. Now it is of this general form. I'll quickly go over this because it's just very technical, and these expressions don't look particularly illuminating. So we have a VA where the numerator is this R product and the denominator is this one, and you can readily verify that this is elliptic. It's an elliptic function in X. And here's the additive coefficient, which needs a whole slide, and it looks really very, very strange, and you wonder how you could ever arrive at this, but Jan-Philippe van Dien did. Well, I'll have a little more to say about this at the very end. Here then you have elliptic functions, and that's then clear that if you switch the A plus and A minus in the way we've seen before, that the operator you get is commuting with the one that you had. Now it's obvious from the expressions that you have D8 invariance. You see that you have invariance under permutations and even sign flips, and that you have formal self-joiners. What is nice here is that the J of the non-relativistic case becomes something that shows that there is an E8 around, because this is nothing else as the reflection in the root that you need to toss into the root system of D8 to get E8. So if you combine this with the other reflections, you get the Weil group of E8. And the kernel is now of this structure here, because we have this U function. It's just in terms of the special function here and the Harshchandra functions. The kernel identity is gotten, now I'm saying just 2 words about how you prove these things, is gotten by having these shifts act on the kernel here. So you're shifting the G function. What you get, you divide by the G function. That gives you something in terms of R functions, and then you use the pole zero, the pole techniques that I described before. Now, and this then has as a consequence that this function here is actually E8 invariant. That's not something that stares you in the face, to put it mildly. Now, this then, with considerable work, can be used to show that there is actually E8 spectral invariance. This is still partly in the works, because right now I still have trouble with an exceptional variety that comes from the fact that you cannot use this Stone-Weierstrass argument here to get the trivial kernel for all of the polytope that's involved here. So that's why there's still some work to be done. I'm still working on this paper, whereas all the previous results are in 2 papers in Communications and Mathematical Physics and 1 in the journal Sigma, the proceedings of the Bonn Conference on Elliptic Integrable Systems of last year. Now let me finish by 2 slides on the n bigger than 1 case. First of all, the kernel identities have only been shown for the defining Hamiltonians there. You expect them to hold for all of the commuting Hamiltonians, but it simply hasn't been shown yet. Then the other thing I mentioned already, you cannot completely arbitrarily choose the couplings. You need to have the extra coupling depend on the previous ones in a linear way. It's a balancing condition. And well, it's obvious that it should be also true for the higher Hamiltonians, but there simply is no proof yet. And possibly along the lines of showing these identities in a very different way, which was found by Komori, Naomi, and Shiraishi recently, there is a way to also handle the higher Hamiltonians, but in this paper only the defining Hamiltonian, even for the AN case, is treated. This is a very beautiful paper where actually it's not just a kernel that connects systems with n particles and n particles. You can have different particle number. So this is genuine generalization, and they use these results to in particular get new results about the Kornminder polynomials, because their scheme is completely uniform in the elliptic, trigonometric, and rational case. They just use the Riemann relation as a main tool to arrive at these identities. There's a certain identity you can find in Whittaker-Watson, which is generalized slightly, and the idea is you blow it up with many, many variables, and then you substitute appropriately, and then there is a way to see that this Van Dien operator comes out, which sort of then you understand why it's there, why it has this funny structure. It's from their point of view much more natural, but still they wouldn't have gotten these identities without sort of knowing that they're there and seeing that you can get them in a very different way. So the explanation for why these things are there is still lacking. Now, last slide. There's still work to do here. What is expected is that you get this spectral invariance in the AN-1 case, and for the BCN case, it's not even clear formally what to expect as regards the spectral invariance properties. Thank you.
Two small questions. You mentioned OI reducing to hypergeometric up to a pullback. Is it some rational pullback, or because in general it's known the theory of giraffe from geometry, differential operators that you can actually perhaps that work conjecture you can reduce to hypergeometry up to rational pullback. So that's my first question.
I'm not clear on your question yet. What exactly do you get via the pullback?
Your own or Kasakov or whatever reduced to hypergeometric up to change of the argument. What was the argument? Was it the rational one or that's?
It doesn't reduce to hypergeometric function in any way. Now, I was mentioning the hypergeometric function in connection with the work of Erdely, where he found a kernel that involves the hypergeometric function, okay, which is of a completely different nature than the one from the talk here, which involves the Jacobi theta functions.
Okay.
There are a priori infinitely many such kernel functions, because if you have the Hilbert space eigenfunctions, then if you look at expressions like this, so let's label them with just some n. You can take arbitrary lambda n's, here are the eigenfunctions, and this type of kernel, when it's convergent, when the lambda n are nicely decaying, will have these properties. But you cannot expect in general, or even at all, that you are able to express such a kernel by choosing appropriate lambdas in terms of previously known functions. This is really the surprise of what's going on here, that there are some choices of these lambda n's such that you get very different functions as a representation of this sum, of this infinite series. And the first result along those lines was by Erdely for the Hoyne case, where this becomes a kernel that involves the 2f1 function.
And my second
Yeah.
question was, clearly you floated with elliptic curves here with two periods. We know that we have a selected situation corresponding to complex multiplication. Complex multiplication pop out at some time as a physical singular selected situation, or you?
I have not looked at this sort of question at all, but these are interesting questions. Yeah, I mean, this is another choice actually for the p-function periods where you also get reality, which is when you take them under the same angle in the complex plane, right? That's a question along those lines as well, where you certainly get reality, but I have not looked at that particular case. So complex multiplication in particular, no. I don't know what special properties that would entail.
Well, let's leave any further questions until coffee, because it's time. We'll resume again at 11:30. Just remains to thank Simon again.